There is a rule written underneath everything we know about the universe, and almost nobody ever talks about it. It says that if you pull back far enough, the cosmos goes smooth, no center, no edge, no special place, the same gentle sameness in every direction forever. Astronomers even gave the scale where the lumpiness is supposed to run out a name. They called it the end of greatness. And then, out toward 2 constellations you can find on a summer night, something turned up that the rule says should not be able to exist. A single connected structure roughly 10 billion light years across, about 1/10 of everything we can see. It is not slightly too big. It is the largest thing we have ever found, by a margin that borders on the absurd. So what happens to a universe with no center, when the biggest object inside it appears to break the very rule that keeps it centerless? Get comfortable and settle in. Subscribe if you have not, because tonight's journey goes to the place where the largest map we have ever drawn starts whispering that the map might be wrong. Let's get into it. Part 1. The rule that makes the universe make sense. There is a rule written underneath everything we know about the universe, and almost nobody ever talks about it. It does not have a dramatic name. It will never be the subject of a blockbuster. But it is the quiet foundation that lets us say anything at all about the cosmos beyond our own backyard. And tonight, very gently, we're going to watch the largest object ever found lean its full weight against that rule and ask whether it can hold. The rule is this: on a large enough scale, the universe is the same everywhere, and it looks the same in every direction. That is the whole thing. Astronomers call it the cosmological principle, which sounds grand, but the idea behind it is almost humble. It says that you are not special. The patch of space you happen to occupy is not the center of anything. There is no edge out past the farthest galaxies, no wall, no rim where the universe stops and something else begins. Pick any galaxy, anywhere, and an observer standing on a planet there would see roughly the same thing you see, in roughly the same proportions, in whatever direction they happen to look. The universe, in other words, has no favorites and keeps no secrets about where the middle is, because there is no middle. Now, that cannot be literally true at small scales, and you already know this just by looking up. The night sky is not smooth. There are stars and gaps between stars. There are bright bands of the Milky Way and dark patches where dust hides the light behind it. Zoom out from our galaxy, and you find that galaxies themselves are not sprinkled evenly through space like sugar on a table. They gather, they clump into groups, and the groups gather into clusters, and the clusters string themselves along enormous threads of gas and dark matter that astronomers call filaments. Between the filaments lie the great empty rooms of the universe, the voids, where you could travel for hundreds of millions of years and pass almost nothing at all. Seen this way, the universe is not smooth in the slightest. It looks like foam. It looks like a sponge. It looks like a web spun by something that worked at a scale we have no words for. So the cosmological principle does not claim the universe is smooth up close. It claims something more subtle and, in a way, more beautiful. It claims that if you back far enough away, all that structure averages out. Think about a sandy beach. Get down on your hands and knees and the beach is nothing but chaos, a jumble of individual grains, each one a different size and shape with little hollows and ridges and the occasional broken shell. There is no order down there at all, but stand up, walk back to the road and turn around, and the beach becomes a single smooth band of tan stretching off in both directions. The grains have not gone anywhere. You have simply pulled back to a scale where their individual lumpiness no longer matters, where the average takes over and the texture disappears. The universe is supposed to do exactly this. The galaxies and clusters and filaments are the grains of sand. They are messy and clumped when you look at any one neighborhood. But the principle promises that somewhere, as you keep pulling back, you reach a scale where the clumping smooths into a uniform haze, where one enormous region of the cosmos becomes statistically identical to any other enormous region, where the foam finally turns into milk. Astronomers even have a half-joking name for the place where this is supposed to happen. They call it the end of greatness. Below that scale, you find great things, structures worthy of the word. Above it, greatness ends. There is nothing bigger to find because the universe has run out of ways to be lumpy, and from there on it is just the same gentle sameness in every direction. Forever. Hold on to that phrase because we are going to come back to it more than once tonight, and by the end it is going to mean something very different than it means right now. The end of greatness. For most of the last century, astronomers have placed that boundary at somewhere around 300 million light-years. That is the scale, give or take, at which the lumps were thought to run out. To say that out loud is already a little staggering. 300 million light-years is a distance so enormous that light itself, the fastest thing there is, needs 300 million years to cross it. Whole species rise and vanish on Earth in less time than that. And yet, on the scale of the whole universe, 300 million light-years is supposed to be the size of the very last grain of sand, the largest the texture is ever allowed to get before smoothness takes over. You might reasonably ask why anyone believes this. It is not a guess, and it is not a matter of taste. The cosmological principle earns its place because the evidence for it is genuinely good. When we look at the oldest light in the universe, the faint glow left over from when the cosmos was only a few 100,000 years old, we find that it is astonishingly even. In every direction that glow has almost exactly the same temperature, matching to within a few parts in 100,000. The early universe, the canvas everything else was painted on, was about as smooth gets. And when we survey millions of galaxies across the modern sky and ask whether one half of the heavens is denser than the other, the answer comes back no. Pull back far enough, and the universe really does seem to settle into that uniform haze the principle predicts. So this is not a fragile assumption that we tolerate because it is convenient. It is a well-supported description of reality, and we lean on it for almost everything. The equations that describe an expanding universe, the ones that let us run the clock backward to the Big Bang and forward to the universe's distant future, only work if the cosmos is smooth and the same in every direction. The claim that the universe has no centre rests on it entirely. The claim that there is no edge to fall off of rests on it. When a cosmologist tells you the Big Bang happened everywhere at once, not at some particular point in space you could fly back to and visit, they are speaking the language of this principle. Take it away, and the most basic furniture of our picture of the universe starts to slide across the floor. And that is exactly why what we are about to talk about is not a small curiosity. Somewhere out in the direction of two constellations you can find on a summer night, Hercules and the little crown beside it called Corona Borealis. There appears to be a single connected structure so enormous that it does not just bump against the end of greatness, it sails clean past it. It is, by the most common estimate, around 10 billion light-years across, not 300 million, 10 billion. More than 30 times longer than the largest thing the rule says should be able to exist. If that number is real, then either the end of greatness is in the wrong place, or there is something about how the universe builds its structures that we have fundamentally misunderstood, or the very tools we use to find this thing have quietly lied to us. There is no comfortable option on that list. Each one, if true, would change something we thought was settled. It helps to understand just how recent this idea is, because the cosmological principle was not handed down from the ancient skywatchers. For most of human history, people assumed the opposite. They assumed there was a centre, and that we were near it, or even sitting right on it. The Earth was the middle of everything, and the heavens turned around us. It took centuries of patient, often uncomfortable discovery to move us off that throne. First, the Earth was demoted from the centre of the solar system. Then the Sun was demoted from the centre of the galaxy. Then the galaxy itself was revealed to be one of a great many, drifting in an enormous crowd. Each step was a lesson in the same direction. The lesson that we are not special, that our location is ordinary, that the universe does not arrange itself around us. The cosmological principle is the final and grandest version of that lesson. It says the demotion is complete and total. There is no centre to be near and no centre to be far from because there is no centre at all. And once you accept that, something strange and wonderful follows about the Big Bang itself. People often picture the Big Bang as an explosion at a particular spot, a single point from which everything flew outward into empty space, the way a firework burst from one place in the night. But the cosmological principle forbids that picture, because a single starting point would be a centre, and there are no centres. So cosmologists say something that sounds almost like a riddle. The Big Bang did not happen at a place. It happened everywhere, all at once, in every part of space simultaneously. The expansion is not galaxies flying away from a point. It is space itself stretching everywhere, so that every observer on every world in every galaxy sees all the others receding and feels, quite correctly, that they are at the centre of their own view, while knowing, just as correctly, that their centrality is an illusion shared by everyone. That is the universe the principle describes, and it is a far stranger and more democratic place than the one our instincts hand us. You can test the idea against your own intuition with a simple thought. Stand outside on a clear night and look up, and you will feel, unavoidably, that you're at the centre of a great dome of stars, that the sky arches around you, and you sit at its middle. Now understand that a person standing on a world in the farthest galaxy you could ever detect would feel exactly the same thing, with exactly the same conviction, looking out at their own dome of stars with themselves at the centre. You're both right about the feeling, and both wrong about the conclusion. The sense of being central is real and universal, and shared by every possible observer, which is precisely how we know it points to no real centre at all. A property that everyone has is not a special property. The cosmological principle takes that small nightly experience, the feeling of being in the middle, and shows that it is the most ordinary thing in the universe, true everywhere and therefore meaningful nowhere. That is the rule the larger structure may be bending, and you can feel its strangeness just by stepping outside and looking up. For tonight, though, set the alarm bells aside. We're not here to be frightened. We're here to follow a genuine mystery patiently, the way you would follow a trail of footprints across fresh snow, noticing each detail, in no hurry to reach the end. And the first thing we need to understand is not the structure itself. It is the strange and almost poetic way it was discovered, because nobody set out to find the largest object in the universe. They found it by accident, while studying the brightest depths in the cosmos, by reading a map drawn entirely in the light of stars that had already been gone for 10 billion years. To understand how that is even possible, we have to talk about what happens when the biggest stars die, and why their final moments make them the best surveyor's stakes the universe has ever offered us. Part 2. Lighthouses made of dying stars. Imagine the most violent thing you can picture, and then understand that the universe does something far past it on a regular basis, somewhere out among the billions of galaxies, roughly once a day as seen from Earth. We call these events gamma-ray bursts, and for a few seconds at a time they are the brightest objects in the entire universe, outshining everything else that exists, all at once, combined. To map the largest structure ever found, we first have to fall in love with these flashes a little, because they are the lamps that lit the way. A gamma-ray burst is, in the most common case, the announcement that a truly massive star has reached the end of its life. Stars spend their lives in a kind of standoff. Gravity is forever trying to crush them inward, and the nuclear fire burning in their cores pushes outward and holds gravity off. For most of a star's existence, those two forces balance, and the star simply shines, patient and steady, for millions or billions of years. But the fuel does not last forever. When a star many times heavier than our Sun finally burns through the last of what it can fuse, the outward push collapses in an instant, and gravity, which has been waiting the whole time, wins all at once. The core falls in on itself and becomes a black hole, and the collapse is so sudden and so catastrophic that the dying star fires two narrow jets of material straight out from its poles at very nearly the speed of light. Those jets are the burst. When one of them happens to be aimed in our direction, even from most of the way across the observable universe, our detectors light up with a flood of gamma radiation, the most energetic form of light there is. And here is the number that should make you sit very still. In the few seconds that a long gamma-ray burst lasts, it can release about as much energy as our sun will radiate across its entire lifetime. Not a year of sunlight, not 1,000 years. The sun's whole existence, all 10 billion years of its burning, from the day it's switched on to the day it will finally fade, compressed into a flash that lasts about as long as it takes you to read this sentence. That is one dying star, saying one last thing and saying it loudly enough to be heard across the whole of creation. Now, you can perhaps see why these events are so useful to us, and why anyone studying the shape of the universe would care about them. Most things in space are far too dim to see from truly enormous distances. A galaxy that is comfortably visible nearby fades into nothing if you push it back far enough. But a gamma-ray burst is so absurdly bright that we can detect it from across almost the entire visible universe, from times so early that the cosmos was a small fraction of its present age. A burst is a flag planted in the distant past, bright enough that the flag never dims no matter how far away it is planted. And because long gamma-ray bursts come from massive stars, and massive stars form in places where there is a lot of gas and a lot of star formation, which is to say in places where there is a lot of matter, the bursts trace something important. They are rough markers of where the stuff of the universe was concentrated. Find a region with an unusual number of bursts, all at about the same distance, and you may well be looking at a region that held an unusual amount of matter when that light set out. The bursts are not the structure. They are pins stuck into the structure, the way you might stick pins into a map to mark every town along a coastline. Count the pins, see where they cluster, and you start to see the shape of the land underneath them. To gather these pins, humanity built machines and lofted them above the atmosphere, because gamma rays are blocked by our air and never reach the ground, which incidentally is very good news for life on Earth. Two of these machines matter most for our story. One is a satellite called Swift, designed to whip around and point at a burst within seconds of detecting it, fast enough to catch the fading afterglow before it disappears. The other is the Fermi Gamma Ray Space Telescope, watching enormous swathes of the sky at once. Between them and the observatories that follow up their alerts, astronomers have built up a catalogue of bursts, and for a fraction of those bursts they have managed to measure not just the direction, but the distance, which is the hard part and the crucial part. A pin with no distance tells you which way to look, but not how far. A pin with a distance tells you where the town actually sits. By the early 2010s, that catalogue of bursts with measured distances had grown to a few hundred entries. It is worth pausing on how precious each of those few hundred is. Every single one represents a star many times the mass of our sun, in some galaxy we will never name, collapsing into a black hole and firing its final cry across billions of years of space and time, only for that cry to arrive at a particular instant at a particular detector, built by a curious species on a small wet planet. Each pin in the map is a funeral we were lucky enough to witness, long after the morning was over, long after the galaxy that hosted it had drifted on and changed beyond recognition. We are reading the obituaries of giants, and from those obituaries we are trying to draw the layout of the universe. There is something almost unbearably poignant about using these particular events as our markers, and it is worth sitting with for a moment rather than rushing past. The stars that produce these bursts are the giants, the ones born with dozens of times the mass of our sun, and giants live fast and die young. A star like our sun will shine steadily for around 10 billion years, a patient and unhurried life. But the truly massive stars burn through their fuel in only a few million years, a cosmic eye blink, blazing furiously and then collapsing while the universe is still young around them. So when we map the cosmos with gamma-ray bursts, We are mapping it with the deaths of the universe's most short-lived and extravagant children, the stars that chose brilliance over longevity and paid for it almost immediately. Consider what the light itself has been through to reach us. A burst out at the distance we care about tonight set off when the universe was only about a quarter of its present age. Its flash has been travelling toward us for around 10 billion years, crossing an expanding ocean of space the entire way, riding through the gulfs between galaxies, passing through the eras when the Sun and the Earth did not yet exist, and would not exist for billions of years more. The light that triggers our detectors set out before there was anyone here to detect it, before there was a here at all in any meaningful sense, and it arrived to find a civilization that had, in the last few decades, just barely learned how to catch it. There is a kind of appointment kept across 10 billion years in every one of these flashes, a message sent by a dying giant into an empty future, received at last by the only species we know of that ever learned to read it. And the reading is harder than it sounds, which is part of why each measured burst is so precious. Catching the flash is only the beginning. To turn that flash into a pin on a three-dimensional map, astronomers must scramble other telescopes to the same patch of sky within minutes or hours before the afterglow fades to tease out how far the burst actually travelled. Most bursts never get that follow-up in time. The few hundred that do, the ones with measured distances, are the survivors of a brutal observational filter, and they are all we have to work with. The map of the largest structure in the universe is drawn from a few hundred lucky funerals, caught in the act, measured against the clock, before their light slipped away forever. There is one more thing these bursts can do that makes them irreplaceable, and it concerns just how far back they let us see. Ordinary galaxies, even bright ones, fade beyond detection if you push them far enough into the distance. Their light spread too thin across the expanding gulf to register. But a gamma-ray burst is so violently luminous that it punches through that limit, remaining detectable from eras when the universe was very young indeed. This means the burst can map regions and times that almost nothing else can reach. The difficult middle distances where galaxy surveys begin to struggle, but where a great deal of the universe's structure was being assembled. The Hercules and Corona Borealis structure lives in exactly that hard-to-reach zone, at a distance and an age where our other tools grow weak, and the bursts are among the few markers bright enough to plant a flag. That is both the strength of the discovery and, as we will see, part of its difficulty, because the very region where the bursts are most useful is also a region where we have few other ways to check what they are telling us. That is the tool. That is the strange and gorgeous method. We map the cosmos with the light of the largest things that have ever died. And it was while sorting through exactly this kind of map, in the direction of Hercules and Corona Borealis, that three researchers noticed something they were not looking for, something that should not have been there, a place where the pins were packed far more tightly than anywhere else in the sky. To understand what they saw and why it stopped them, we need to go back to the year it happened, and to the quiet, almost reluctant way that the largest object in the universe first announced itself. Part 3. A Clump in the Catalogue. In the year 2014, three astrophysicists were doing the kind of careful, unglamorous work that most real science is made of. Their names were Istvan Horvath, Jon Hakila, and Zsolt Bergoli, and they were not hunting for the largest structure in the universe. Nobody hunts for such a thing, because nobody expects it to be findable. What they were doing was more modest and more methodical. They were studying the way gamma-ray bursts are distributed across the sky, asking a straightforward question that statisticians ask about almost everything. Are these flashes scattered randomly, the way raindrops fall on pavement, or is there some pattern hiding in where they appear? This is a sensible thing to check, and for the most part the answer the universe gives is reassuring. If you take all the gamma-ray bursts ever recorded, spread across all distances, and ask whether they favour any particular part of the sky, the answer is essentially no. They come from everywhere, fairly evenly, which is exactly what the cosmological principle predicts. The deaths of massive stars happen all over the universe because matter is, on the larger scales spread all over the universe. So far, so smooth. So far, the rule holds. But Horvath and his colleagues did something more refined than lumping all the bursts together. They sorted the bursts by distance, which is to say by how far back in time they were looking, and then they examined each slice of cosmic history on its own. This matters, because a clump at one distance can be completely hidden if you blur it together with everything in front of it and behind it. It is like trying to notice that one particular floor of a skyscraper is unusually crowded while looking at the whole building from outside. The crowd vanishes into the average. You have to look floor by floor to catch it. When they looked floor by floor, one slice of the universe refused to behave. It sat at a distance corresponding to a light travel time of around 10 billion years, in a band of cosmic history when the universe was only about 3 to 4 billion years old, less than a third of its current age. And in that slice, in the direction of the constellations Hercules and Corona Borealis, there were simply too many bursts. Where a smooth, well-behaved universe would have scattered perhaps a handful of bursts across that patch of sky at that distance, the data showed a tight concentration, a cluster of somewhere between 19 and 31 bursts crowded into a region far smaller than they had any business occupying. The pins were not spread across the map, they were jammed into one corner of it. To grasp why this stopped them cold, you have to remember what each of those pins represents. Every burst marks a region where massive stars were forming, which marks a region where matter had gathered. A few bursts close together might be coincidence, the same way you can flip a coin and get 3 heads in a row without anything being wrong with the coin. But a concentration this strong, in this narrow a slice of distance, in this small a patch of sky, is not so easily waved away. It suggested that, 10 billion years ago, in that one direction, there was a region of the universe positively crowded with the machinery of star formation, a place where matter had assembled in quantities and across distances that the smooth universe was not supposed to allow. The 3 researchers ran the statistics. They asked the question every careful scientist asks before getting excited. What are the odds that a random, smooth universe would produce a clump this tight purely by chance? And the odds, by their analysis, were low enough to take seriously, low enough to suggest that this concentration of bursts was tracing something genuinely real, an actual overdensity of matter rather than a trick of random scatter. They wrote it up carefully and published it, and the title of their paper was almost comically restrained for what it contained. They called it, in effect, a possible structure in the gamma-ray burst sky distribution. Possible. A single cautious word doing an enormous amount of work, because what they were describing, if it was truly a single connected structure, would be the largest object ever identified by human beings, by a margin that bordered on the absurd. It is worth lingering on that restraint because it tells you something about how good science actually behaves when it brushes up against something extraordinary. They did not announce that they had broken cosmology. They did not declare the cosmological principle dead. They reported a clustering, gave their best estimate of its significance, and used the word possible, leaving the door open for the universe to surprise them in either direction. That caution is going to matter enormously later in our story, because the reality of this structure has been argued over ever since, and the people doing the arguing are not cranks. They are exactly the kind of careful researchers who use words like possible. It is worth dwelling on why sorting the bursts by distance was the crucial and clever move, because this is the kind of methodological choice that separates a real discovery from a missed one. Imagine you're trying to find out whether a particular floor of a tall apartment building is unusually crowded. If you simply stand outside and count every lit window across the whole face of the building, you will get an average, and that average will hide everything interesting. A crowded floor and an empty floor will blur together into a perfectly ordinary-looking building. The only way to catch the crowded floor is to examine the building floor by floor, to slice it into layers and study each layer on its own. The bursts are the lit windows, the distance is the floor, and the universe, examined floor by floor, turned out to have one floor in the Hercules and Corona Borealis direction that was crowded in a way no smooth model would allow. The cluster they found also raises a question that is easy to overlook but genuinely important, which is what it would even take to produce so many massive star deaths in one region at one time. Long gamma-ray bursts come from the collapse of giant stars, and giant stars form in regions actively building new stars at a furious rate, which in turn requires enormous reservoirs of gas, which in turn requires a great deal of matter gathered into one place. So a concentration of bursts is not just a concentration of explosions, it is the visible tip of a much larger concentration of everything, of gas and dust and dark matter, and the gravitational machinery of star formation, all gathered into one corner of the young universe across a span that, when measured, refuses to fit inside the rules. The bursts are loud, but they are pointing at something quiet and enormous underneath, the way a scattering of lighthouses along a coast points at the dark mass of a continent you cannot see in the night. It is also worth appreciating the restraint of using the word possible in a scientific title, because that single word carries a quiet kind of courage. It would have been easy and tempting and far more attention-grabbing to announce flatly that the largest structure in the universe had been found, full stop, no hedging. The discovery would have made headlines around the world either way, but the three researchers chose the honest word, the careful word, the one that left room for the universe to prove them wrong. That choice tells you something about how trustworthy science actually works at its frontier. The people most qualified to be excited about a result are often the most careful about overclaiming it, precisely because they understand its weaknesses better than anyone. When you encounter a scientist who hedges, who says possible where a showman would say certain, you're usually looking at someone who takes the truth more seriously than the attention, and that hedging is not weakness. It is the sound of integrity working in real time, and it is the reason we can trust the field to eventually sort the real structures from the illusions, however long it takes. But before we get to the doubts, we have to reckon with the sheer scale of what they had found, because the number that came out of those crowded pins is the number that makes this whole story matter. When you take that concentration of bursts and measure how far it extends across space, you arrive at a figure that is genuinely difficult to hold in the mind. The structure traced by those bursts appears to stretch something like 10 billion light-years from one side to the other. And to understand what 10 billion light-years means, to really feel it rather than just hear it, we have to do something almost violent to our sense of scale. We have to take the entire observable universe, the whole of everything we could ever see, and shrink it down until it fits in your hands, and then go looking for this thing on its surface. When we do that, something happens to the comfortable rule from the beginning of tonight's journey, and it does not survive the comparison intact. Part 4. The size. Nobody was ready for. Let me try to give you this number in a way that actually lands, because if I simply tell you the structure is 10 billion light-years across, your mind will file it away next to every other enormous number you have ever heard and move on, and that would be a kind of tragedy. Numbers this large stop meaning anything precisely because they are so large. So let us not just hear it. Let us build a model of it together, slowly, and stand inside the result. Take the entire observable universe, everything, every galaxy whose light has had time to reach us since the beginning, every cluster, every void, every filament, all of it, out to the farthest horizon in every direction. That whole thing measures about 93 billion light-years from one side to the other. Now shrink it. Shrink it down in your imagination until the entire observable universe is the size of a basketball, sitting in your hands, light enough to spin on one finger. Everything that exists, that we could ever observe, now fits inside a sphere you could carry under one arm. At that scale, where do you fit? Where is our galaxy, the Milky Way, the great wheel of 400 billion stars that contains our sun and every human being who has ever lived and everything any of us has ever touched or seen? On the surface of that basketball, the entire Milky Way is far smaller than a single atom. You could not see it. You could not find it with the finest microscope. The galaxy that holds absolutely everything you have ever known is, At this scale, less than a speck within a speck, an immeasurable nothing on the skin of the ball. Now go looking for the structure we have been describing, the concentration of bursts out toward Hercules and Corona Borealis. By the common estimate, it is about 1/10 of the diameter of the whole observable universe. So on your basketball, where the Milky Way is smaller than an atom, this thing is not a speck at all. It is a feature you can see with your eyes. It runs across roughly 1/10 of the surface of the ball, a faint bright seam that you could trace with the tip of your finger, a continent-sized marking on a world where entire galaxies have shrunk past the point of visibility. You're holding the universe in your hands, and there is a single connected structure on it large enough to touch. Sit with that image for a moment, because it contains the entire problem in miniature. The rule we began with, the cosmological principle, the end of greatness, all of it comes down to a promise that there should be nothing on that basketball big enough to see. Pull back to the scale of the whole universe, and you are promised a smooth, featureless ball, a uniform haze with no markings, no seams, no continents. The whole point was that greatness ends, that the lumps run out, that from far enough away the cosmos is as plain and even as a billiard ball, and instead, when we actually look, there is a marking on it the width of a fingertip, a thing we were assured could not be there. Let me put the comparison in the bluntest possible terms, the way the researchers themselves had to confront it. The larger structure the standard rules of cosmology say can exist, the biggest grain of sand before smoothness takes over, is somewhere around 1,200,000,000 light-years across at the very most, and many estimates put the limit lower. The Hercules and Corona Borealis structure, if the bursts are tracing what they appear to trace, is around 10 billion light-years across. Divide one by the other, and you find that this thing is somewhere between 6 and 9 times larger than the absolute ceiling. It is not nudging the limit. It is not a borderline case that slightly exceeds expectations. It is multiple times past the line, the way a single mountain would be multiple times past the height of every grain of sand on a beach you had just declared perfectly smooth. And the strangeness deepens when you remember when this light is from. We are not seeing this structure as it would be today. We are seeing it as it was around 10 billion years ago, when the universe was young, only about 3 to 4 billion years past the Big Bang. In the standard story of how the cosmos assembles itself, structure grows slowly. It takes time for gravity to gather matter, to pull the gas and the dark matter together into clumps and then into clusters, and then into the long threads of the cosmic web. The early universe is supposed to be less structured than the universe today, not more, because there has been less time for gravity to do its patient work. So a structure this enormous is not just too big, it is too big too early. It is as if you walked into a room, found a sandcastle the size of a house, and were then told that it had been built in the first 10 minutes after anyone arrived on the beach. The size alone is a problem. The size combined with the youth is something close to an impossibility, at least according to the rules as we have written them. This is the moment in our story where the comfortable cosmos from part 1 starts to feel less comfortable. We began with a universe that was smooth and centerless and reassuring, a place where you were promised you held no special position because no position was special, where the sameness in every direction was a kind of quiet companionship across the emptiness. And now there is a crack running through that picture, a single object that the picture says should not be allowed, hanging in the young universe at a size that beggars the imagination. The rule has not broken yet. We're going to spend the rest of tonight examining whether it really is breaking and what it would mean if it were. But the crack is there, and you can feel it, the same way you can feel a single wrong note in a piece of music even before you can name what was wrong. There is a second way to feel this scale, and it has to do with time rather than distance, because in cosmology the two are the same thing wearing different clothes. When you look at something 10 billion light-years away, you are not seeing it as it is now. You're seeing it as it was 10 billion years ago, because that is how long its light took to cross the gulf to your eye. So the structure we are describing is not a snapshot of the present universe at all. It is a snapshot of the ancient past. a region as it appeared when the cosmos was young, frozen in the light that has only just now finished its journey. Whatever those galaxies became in the 10 billion years since, whatever they are doing right now in whatever counts as the present out there, we will not know for another 10 billion years, long after our sun has died. We're not looking across space so much as down through time, reading a layer of the universe laid down when the Earth was not even a possibility yet. And this is where the trouble compounds, because the structure is not only enormous, it is enormous in a chapter of cosmic history when enormity had barely had time to assemble. Picture the universe's history as a single year, with the Big Bang on the first instant of the 1st of January, and the present moment at the last stroke of midnight on the 31st of December. On that calendar, the light we are seeing from this structure left its sources somewhere around the start of April, when the universe was only a third of the way through its life. The slow, patient gathering of matter by gravity, the process that builds all large structures, had been running for only a few of those calendar months. And yet there, in early April, sits a structure that even the full year was not supposed to be enough to build. It is not merely a sandcastle too large for the beach. It is a sandcastle too large for the beach, found at a time when the tide had only just gone out and the sand was barely dry. Let me offer one more comparison, because the number deserves to be felt from as many angles as possible. The distance light travels in a single year is already almost beyond imagining, around 6 trillion miles, a figure you cannot picture and neither can I. Now multiply that by 10 billion to reach across this structure. The result is a distance so large that the word distant starts to feel inadequate, because nothing about human experience prepares us for it. Here is perhaps the only honest way to hold it. The structure is so wide that light, moving at the only speed the universe allows nothing to exceed, needs 10 billion years to cross it, which is longer than the Earth has existed, longer than the sun has existed, nearly as long as the sun will continue to burn before it dies. A beam of light setting out from one edge of this structure, travelling without rest at the fastest speed there is, would not reach the far edge until well after our entire solar system has lived and died. That is not a distance. That is closer to a span of cosmic eternity laid out in space, and it is the width of a single thing. Try, for a moment, to imagine being patient enough to wait out that crossing, to sit at one edge and watch for the beam to arrive from the other. You would wait longer than the age of every rock on Earth. You would wait while new stars were born and died, while whole galaxies rearranged themselves, while the universe itself grew measurably older and emptier around you. And only then, after all of it, would the light finally arrive, having traced the span of one object. That is what we mean, in the end, when we say the word largest. Before we decide whether to trust this thing, though, we owe it to ourselves to understand precisely why the rules forbid it. It is not enough to say a structure this big should not exist. We need to understand the machinery underneath that should not, the actual physics of how the universe builds anything at all, and the hard ceiling that machinery is supposed to place on the size of everything. Because once you understand why the ceiling exists, you understand why a single object poking through it is not a minor record to be broken. It is a challenge to the foundation, and the foundation does not bend easily. Part 5. Why this is not allowed. To understand why a structure this large is forbidden, we have to talk about how the universe builds things, and the story begins not with galaxies, but with the faintest imaginable ripples in an almost perfectly smooth beginning. When the universe was very young, it was very nearly uniform, that glow of ancient light I mentioned earlier matching to within a few parts in 100,000 in every direction, but not perfectly uniform. There were tiny variations, regions that were a hair denser than average, and regions that were a hair emptier. The faint imprint of quantum fluctuations stretched to enormous size in the universe's first moments. Those tiny differences were the seeds of everything that would ever exist. Here is how a seed grows. A region that is slightly denser than its surroundings has slightly more gravity, because gravity comes from matter, and that region has a little more matter. That extra gravity pulls in a little more material from nearby. Now the region is denser still, so its gravity is stronger still, so it pulls in even more. This is a runaway process, slow at first and then faster, the dense growing denser across cosmic time. Over billions of years, those faint initial ripples grow into the galaxies and clusters and filaments we see today. Everything that has any structure at all was once just a slight excess, a gentle lean in the density that gravity spent eons amplifying. But this process has a built-in speed limit, and the speed limit is where our problem lives. Gravity does not act instantly across any distance. Its influence travels, ultimately bounded by the speed of light, the same cosmic limit that governs everything. So for a region of space to gather itself into a single connected structure, the different parts of that region have to have had time to feel each other's gravity, to communicate, to fall together. The larger the structure you want to build, the more time you need, because gravity has to reach across the whole thing to pull it into one piece. And the universe has only existed for a finite time, around 13.8 billion years. That finite age, combined with the finite speed at which gravity can coordinate matter, sets a hard ceiling on how large any single coordinated structure can possibly be. Astronomers have done this calculation carefully, working within the standard model of the universe, the one with its particular recipe of ordinary matter, and dark energy. And the answer they get for the largest structure that should be able to form is somewhere around 1,200,000,000 light-years across, with many analyses landing well below even that. Above that scale, there simply has not been enough time since the beginning for gravity to assemble anything into a single connected whole. Above that scale, the universe is supposed to transition into smoothness, into that uniform haze, because the lumps cannot grow any larger no matter how patient gravity is. That ceiling is the physical meaning of the end of greatness. It is not an arbitrary line drawn on a chart. It is the consequence of the universe having a finite age and gravity having a finite reach. Now you can see the full weight of the problem. The structure out toward Hercules and Corona Borealis is 6 to 9 times larger than that ceiling. If it is a single connected structure, then gravity somehow assembled something far larger than gravity had time to assemble. The math does not merely frown at this. The math says it cannot happen, not in the universe as we have modelled it, not with the amount of time available, not with the speed at which gravity coordinates matter. Something is wrong. Either the structure is not what it appears to be, or the model that produces that ceiling is missing something important about how the early universe behaved. And here is where I want to slow all the way down, because this is the emotional centre of why this story matters, and it has nothing to do with the structure being big and frightening. It is not frightening at all. It will never touch us. It sits 10 billion years in the past, unimaginably far away, utterly indifferent to whether humanity ever noticed it. The weight of this is not danger. The weight is what the structure threatens to take away from us, which is the quiet promise we started with. Remember that promise. The cosmological principle is the reason you're not standing at the edge of anything. It is the reason you're not falling towards some cosmic centre, the reason your location in the universe is ordinary and therefore, in a strange way, never lonely, because ordinariness means you're not isolated in some special pocket, but woven into the same fabric as everything else. The smoothness of the universe is what makes it feel like a home rather than a labyrinth. It is the guarantee that the cosmos has no favourites and keeps no secret middle, that wherever you go, the universe greets you the same way. And the largest object we have ever found is the first thing big enough to make serious scientists ask, out loud, in print, whether that guarantee actually holds. The thing that lets the universe have no centre may be quietly broken by the largest thing inside it. That is the real vertigo here, not the size. The possibility that the rule which made us feel at home in an enormous universe might not be a rule at all, but only a habit the universe has mostly kept, until now. It is worth being precise about what gravity is actually fighting against in the early universe, because it is not only the shortage of time, It is also the expansion of space itself. While gravity is patiently trying to pull matter together into clumps, the whole universe is stretching, carrying everything apart, working directly against the gathering. Building a structure by gravity is therefore a little like trying to assemble a pile of marbles on a rubber sheet that is being stretched in every direction at once. The marbles you have already gathered tend to stay together because their mutual pull is strong, but reaching out to gather marbles from further away becomes harder and harder as the stretching carries them off. This is part of why there is a ceiling on structure size at all. Beyond a certain scale, the expansion wins, pulling regions apart faster than gravity can knit them together, and no larger structure can form no matter how long you wait. So when we say the Hercules and Corona Borealis structure is 6 to 9 times larger than the ceiling, we are not saying gravity merely ran out of time. We are saying gravity would have had to overcome the relentless stretching of space across a span where that stretching should have made gathering impossible. The structure is not just early and large, it is large in precisely the regime where largeness is supposed to be forbidden twice over, once by the shortage of time and again by the expansion tearing distant regions apart. That double forbidding is why this is not a small anomaly that a minor adjustment could absorb. To allow it, you have to change something fundamental, either about how fast structure can grow, or about how the early universe was seeded, or about the nature of the expansion itself. And yet I keep returning to the strange gentleness of this crisis, because it is important not to mistake it for a threat. Nothing about this structure endangers us. It is not coming toward us. It does not affect the sun or the earth or the night sky you can walk outside and see. Its entire menace is conceptual, a menace to a sentence in a textbook rather than to any living thing. What it threatens to take is not our safety but our certainty, the comfortable sense that we had the larger scales of the universe figured out. And there is a strange dignity in a species being able to lie awake, not over any danger to itself, but over whether a rule about the shape of everything is precisely true. To be troubled by the size of a structure 10 billion light years away that can never touch you is a very pure kind of curiosity, perhaps the purest there is. It is worth pausing on a subtle point that often gets lost, which is that the ceiling on structure size is not a vague rule of thumb, but something physicists can calculate from the ingredients of the universe. Give them the amount of ordinary matter, the amount of dark matter, the strength of dark energy, and the age of the cosmos, and they can compute with real rigor the largest structure that gravity should have been able to assemble in the time available. That calculation is not a handwave, it is a prediction, made from the same model that successfully explains the ancient glow of the early universe and the overall expansion. So when a structure appears to exceed that calculated ceiling by a factor of 6 to 9, it is not bumping against a soft guideline that we might generously stretch. It is contradicting a specific number that falls out of the same trusted model that gets so much else right. Either the structure is not what it seems, or one of the ingredients we fed into that calculation, the matter, the dark energy, the behavior of gravity, the seeds of structure, is not quite what we believe. There is no third option that leaves everything comfortably in place, which is exactly why the structure refuses to be ignored. I told you we would return to the end of greatness, and we have, but only part way. We have seen why the ceiling exists and why this structure appears to crash through it. What we have not yet faced is the most unsettling fact of all, the one that turns a single strange object into something that looks like a pattern. Because if the Hercules and Corona Borealis structure were the only thing of its kind, a lone giant in an otherwise smooth cosmos, we might be able to call it a freak, a one-in-a-universe accident, and sleep soundly. But it is not the only one. Other things have been found out there, other structures that stretch past the ceiling, and once you see them lined up together, the comfortable explanation of a single fluke becomes much harder to believe. Part 6. It is not alone. The most reassuring thing anyone could tell you right now is that the structure we have been describing is a one-off, a singular accident, the cosmic equivalent of flipping a coin 1,000 times and getting an improbable streak that means nothing. A single anomaly can almost always be explained away. The universe is large, and large things produce rare coincidences, and if you go looking through enough data, you will eventually find something that looks impossible but is merely unlikely. If the Hercules and Corona Borealis structure stood alone, that is almost certainly the story we would tell, and it would be a good story. Unfortunately, it does not stand alone, and the company it keeps is the reason astronomers cannot simply file it away. Let us walk back through the history of the largest things we have found, because there is a pattern in it that is hard to unsee once you have noticed it. For a long time, the title of largest known structure changed hands every so often, and each new record holder pushed the boundary a little further out, closer to and then past the ceiling that the rules were supposed to enforce. In the late 1980s, astronomers mapping the positions of galaxies found an enormous sheet of them stretched across the nearby universe, a structure they called the Great Wall, running for hundreds of millions of light years. At the time, it was the largest known thing in the cosmos, and it already crowded uncomfortably close to the supposed limit. Then, in 2005, a larger one was found, a structure now called the Sloan Great Wall, named for the great survey of the sky that revealed it. It stretched something like 1,400,000,000 light-years from end to end. Already, that single structure was nudging past the most generous version of the ceiling, the 1,200,000,000 light-year limit we discussed. One structure poking slightly past the line could perhaps be tolerated, treated as a rare fluctuation near the edge of what is allowed. But the line had been crossed, and the universe was not finished. In 2013, a year before the Hercules and Corona Borealis structure was announced, astronomers studying quasars found something larger still. Quasars are the blazing cores of galaxies where matter is falling into enormous black holes, and like gamma-ray bursts they are bright enough to be seen across great distances, which makes them useful pins for mapping the far universe. A group of 73 of these quasars was found clustered together into a single enormous association, stretching about 4 billion light-years across. They called it the Huge Large Quasar Group, and the plainness of that name barely conceals how startling it was. 4 billion light-years is more than 3 times the ceiling. Now there were 2 structures past the line, and one of them dramatically so, and the discoveries have kept coming, right up into recent years. Using yet another clever method, reading the fingerprints that intervening gas leaves on the light of distant quasars, an astronomer named Alexia Lopez and her colleagues identified a structure they called the Giant Arc, a curved chain of galaxies and gas stretching around 3,300,000,000 light-years across the sky. And then, more recently still, the same line of work turned up another, a nearly circular structure they named the Big Ring, around 1,300,000,000 light-years in diameter and far larger around its circumference. Different methods, different teams, different parts of the sky, different distances, and the same stubborn result. Structures keep turning up that are larger than the rules say structures can be. When you line them all up, the Great Wall, the Sloan Great Wall, the Huge Large Quasar Group, the Giant Arc, the Big Ring, and the Hercules and Corona Borealis structure towering over all of them, the comfortable explanation starts to wobble. You can call one of them a fluke. You can perhaps call 2 of them flukes if you're feeling generous with your luck. But a whole staircase of structures, each one found by different people using different tools, each one reaching past the ceiling, begins to look less like a series of accidents and more like the universe trying to tell us something. Either the ceiling is in the wrong place, or there is a systematic reason that our methods keep finding structures too large, or the cosmos really does build bigger than our theory of gravity and time allows. None of those is a small statement. I want to be careful and fair here, because honesty is the whole point of how we do things on this channel. Not all of these structures are equally certain, and we will spend real time soon on exactly how shaky some of them are. Several of them have been challenged. Some may turn out to be statistical illusions, chance alignments that look like structures but trace no real concentration of matter. The Hercules and Corona Borealis structure in particular has been argued over fiercely. So this staircase is not a staircase of proven facts. It is a staircase of claims, each one defensible, each one contested, each one sitting at the difficult edge of what our data can actually establish. But that is precisely what makes the pattern interesting rather than dismissible. If only one oversized structure had ever been claimed, we could shrug. The fact that the claims keep arriving from independent directions is the thing that keeps the question alive. What makes the staircase of oversized structures especially difficult to dismiss is that the different steps were found by completely different methods, each with its own personality and its own blind spots. The early Great Wall and the Sloan Great Wall were mapped by surveying the positions of ordinary galaxies, painstakingly measuring the distances to hundreds of thousands of them. The huge large quasar group was traced by quasars, the blazing cores of active galaxies. The giant arc and the big ring were found by an entirely different trick, reading the shadows that intervening clouds of gas cast on the light of quasars far behind them. These methods do not share the same weaknesses. A flaw that fooled one of them would not necessarily fool the others. So when independent techniques, vulnerable to different errors, keep returning the same surprising verdict, that the universe builds structures larger than the ceiling allows, the verdict becomes much harder to wave away as a quirk of any single instrument. There is also a subtler point hiding in this staircase, about the history of the word largest. Notice that the record for the largest known structure has been broken again and again across the decades, and each time the new record holder reached further past the supposed limit. This could mean one of two things, and they point in opposite directions. It could mean that the universe genuinely contains structures of many sizes, including enormous ones, and that we are simply discovering larger ones as our surveys reach deeper, in which case the ceiling is real trouble. Or it could mean that as our surveys cover more sky and more volume, we are giving ourselves more opportunities to stumble onto chance alignments that merely look like structures, in which case the ever-growing record is a sign of our growing ability to fool ourselves, not of the universe's lumpiness. The same pattern supports both the thrilling reading and the deflating one, and which is correct is exactly what we cannot yet decide. I want to underline how unusual it is in science to have a result this important sitting unresolved for this long. Many discoveries are dramatic precisely because they get confirmed or refuted quickly, a clean before and after. But the oversized structures have lingered in the contested middle for years, neither triumphantly verified nor cleanly killed. That lingering is not a failure of the field. It is a sign of intellectual honesty, of a community that refuses to declare victory for either the exciting answer or the safe one until the evidence is genuinely strong enough to compel it. The structures are allowed to remain mysteries because the people studying them are disciplined enough to tolerate not knowing, which is a rarer and harder thing than it sounds. There is a human dimension to this staircase of structures that is easy to miss in the rush of numbers, and it concerns the slow, generational nature of the work. The early Great Wall was found by astronomers patiently measuring galaxy distances in the 1980s, work that took years, and built on the surveys of those who came before them. Each later structure was found by a new generation, using instruments their predecessors could only have dreamed of, standing on the maps the earlier astronomers had drawn. The discovery of the largest structures in the universe is not the work of any single brilliant moment. It is a relay race run across decades, each team carrying the map a little further out, each one pushing the known edge of structure a little closer to and then past the supposed limit. When you look at the staircase, you're not only looking at a series of objects, you're looking at the accumulated patience of several generations of people who spent their careers measuring the positions of faint lights, never quite sure whether they were charting the universe or the limits of their own ability to see it. It also matters that these structures were not predicted before they were found, which changes how we should weigh them. Nobody sat down with the equations of cosmology and said, "Here is where a giant wall should be, go and look for it." Instead, the structures kept turning up unbidden, surprising the very people who found them, emerging from surveys that were designed to study something else entirely. There is a difference between a prediction confirmed and a surprise stumbled upon, and the surprises carry a particular kind of weight. A confirmed prediction tells you your theory is working. A repeated surprise, especially one your theory says should not happen, tells you that either your theory has a gap or your methods have a flaw, and that you will not rest easy until you know which. The oversized structures are surprises, again and again, and a universe that keeps surprising you in the same direction is a universe trying to get your attention. Whether it is pointing at a flaw in the cosmos or a flaw in our looking, the persistence of the surprise is itself the signal worth heeding. And so the mystery sharpens into a genuine fork in the road. Either the universe is lumpier on the larger scales than our most fundamental assumption allows, in which case cosmology has a profound and beautiful problem on its hands, or our tools for finding these structures are systematically fooling us, painting walls and rings and arcs onto a sky that is actually smooth underneath. Both of those possibilities are extraordinary in their own way. To decide between them, we have to do the hardest and most important thing in all of science, the thing that separates a real investigation from a campfire story. We have to turn around and attack our own evidence as hard as we can and ask whether the largest structure in the universe might not be there at all. Part 7. The Case Against the Wall. The most important thing I can tell you tonight is that the largest structure in the universe might not exist, and that the people who argue it does not exist are not skeptics for the sake of being difficult. They are doing the finest and most honest work in the whole story. It is easy to fall in love with a spectacular result. It is much harder and much more valuable to turn around and try to break it. So let us do that now, in good faith, and give the doubt its full and proper weight, because a mystery you're not willing to question is not a mystery at all. It is just a belief. Recall how the structure was found. It was traced by gamma-ray bursts, those lighthouses made of dying stars, those flashes so bright we can see them across most of the universe. Earlier I described them with real affection, and the affection was earned, because there is genuinely nothing else that can light up the far past the way they do. But every tool has a personality, and a good investigator has to know the weaknesses of a tool as intimately as its strengths. The lighthouses are magnificent, but they are not evenly placed, and worse, they are not evenly seen. And those two facts are the hinge on which this entire doubt turns. Start with the smallness of the numbers. The whole detection rested on a cluster of somewhere between 19 and 31 bursts, standing out against the background. That sounds like a fair few, but in the world of statistics it is a perilously small sample on which to hang the largest claim in the history of cosmology. With numbers that small, the line between a real pattern and a random clump is genuinely blurry. Think about flipping a coin. If you flip it 10 times and get 7 heads, you would not conclude the coin is rigged, because small samples are noisy and streaks happen easily. You need a great many flips before an imbalance becomes convincing. The bursts are like a small number of coin flips, and a clump of 19 to 31 of them, however strong it looks, simply does not carry the statistical weight that a claim of this magnitude really demands. Reasonable people can look at that same clump and disagree about whether it is signal or noise, and reasonable people have. Now the deeper problem, the one about the lighthouses not being evenly seen. To map where the bursts truly are, you have to be able to detect them equally well in every direction. But we do not. Our gamma-ray detectors do not survey the whole sky with uniform sensitivity. The satellites that catch these bursts have their own patterns of where they point and how long they linger, favouring some regions of the sky over others simply because of how they were scheduled and how they orbit. On top of that, our own galaxy gets in the way. The thick band of the Milky Way, crowded with stars and dust, blocks and confuses our view of whatever lies behind it, leaving a great stripe across the sky where bursts are hard to catch. And catching a burst is only half the job. To place it in our map, we also have to measure its distance, and that requires fast follow-up with other telescopes, which does not happen equally for every burst in every part of the sky. Put all of that together and you arrive at the core of the skeptical case. if our ability to detect and measure bursts is uneven across the sky, then the burst will appear to clump in the regions where we happen to look most carefully, even if the real distribution of bursts, and therefore of matter, is perfectly smooth underneath. The lighthouses would seem to crowd together, not because the universe placed them together, but because we were standing in a particular spot looking through particular windows with particular blind spots. The cluster could be a portrait of our own observing habits rather than a portrait of the cosmos. The wall could be a shadow cast by the shape of our attention. This is not a hypothetical worry that I'm inventing to seem balanced. Other researchers have taken the same gamma-ray burst data and reanalyzed it specifically to test this concern. Some, looking carefully at how the bursts are sampled and accounting for the uneven exposure of the detectors, have concluded that the statistical significance of the clustering shrinks, sometimes dramatically, when these effects are properly included. The signal that looked compelling in the original analysis softens in their hands towards something that could plausibly be chance. The original authors have defended their result and responded to the criticisms, and the back and forth has continued in the scientific literature for years, which is exactly how it should be. This is not a fight between believers and deniers. It is a careful, technical, ongoing argument about whether a small sample seen through an uneven instrument is telling us about the universe or about ourselves. There is one more honest complication, and it concerns what we even mean by the size of this thing. A galaxy cluster has a reasonably clear core, a centre of mass you can point to. But the Hercules and Corona Borealis structure is not like that. It is a statistical overdensity, a region where the pins are denser than average, with fuzzy and arguable edges. How big you say it is depends entirely on where you decide to draw its boundary, and there is no obvious place to draw it. Stretch the boundary generously, and the structure is gigantic. Draw it conservatively, and it shrinks. So even the famous figure of 10 billion light-years is not a measurement in the way your height is a measurement. It is an estimate that depends on choices, and different choices give different answers. So here is the fair and uncomfortable summary, the one a careful person has to be willing to hold. The Hercules and Corona Borealis structure is a real claim, supported by a real excess of bursts, sitting precisely on the knife's edge of what our current data can establish. It has not been proven, and it has not been refuted. It is the kind of result that lives in the difficult middle ground, too remarkable to dismiss and too uncertain to trust. The kind of result that will only be settled when the catalogue of bursts grows large enough and the maps of the universe grow detailed enough to overrule the noise one way or the other. We do not get to know tonight, and there is something fitting, even beautiful, in not knowing, because it keeps us honest. The largest thing in the universe may be telling us about the shape of the cosmos, or it may be telling us about the shape of our own ability to see. We cannot yet say which. Let me give you a concrete sense of how a perfectly smooth universe could fake a structure, because it is easy to say selection effects in the abstract and never feel the force of it. Imagine an enormous field at night, with fireflies scattered completely evenly across it, no clumps anywhere, a perfectly uniform sprinkle of light. Now imagine you try to map the fireflies, but you can only watch the field through a handful of narrow windows, and some of those windows have clean glass while others are smeared and dim. Through the clean windows you catch many fireflies. Through the smeared windows you catch few. If you then draw a map based only on what you caught, the fireflies will appear to cluster near the clean windows and thin out near the smeared ones, and you might triumphantly announce that you have found a great firefly wall, when in truth the field was perfectly even, and you were only charting the cleanliness of your own windows. Our gamma-ray detectors are the windows, their uneven sensitivity across the sky is the smearing, and the worry is that the wall we found is a map of our windows rather than the field. This is why the small sample size and the uneven coverage are not two separate problems, but one compounded problem, each making the other worse. With a large, evenly gathered sample, a few smeared windows would not matter much because the sheer number of fireflies caught everywhere would average out the unevenness. And with perfectly even windows, a small sample might still be trustworthy. because at least it would not be biased in any particular direction. But combine a small sample with uneven windows, and you get the worst of both worlds. A handful of points seen through a distorting lens, where it becomes genuinely hard to tell whether a cluster is a feature of the universe or an artifact of the viewing. That is the precise corner the Hercules and Corona Borealis structure lives in, and it is why honest researchers can look at the identical data and reach opposite conclusions without either of them being foolish. And here, gently, the lighthouses come back to trouble us, the same image we admired earlier. I asked you, near the beginning, to fall a little in love with these flashes, these lighthouses built from the deaths of giant stars, and the affection was real and earned. But a lighthouse is only useful for mapping a coast if the lighthouses are evenly spaced and you can see them all equally well. If half of them are hidden behind fog and you chart the coastline only from the ones you can see, you will draw a coast that bulges toward the clear air and shrinks into the fog, a coastline shaped by the weather rather than the land. The very thing that made these dying stars such magnificent markers, their brilliance across enormous distances, cannot save them from this problem, because brilliance does not help if the fog of our own galaxy and the unevenness of our own instruments decides which flashes we're allowed to count. The lighthouses are real. The question is whether we are seeing them as they are placed, or only as we happen to be able to look. But suppose, for the sake of following the thread all the way to its end, that the doubters do not win. Suppose the structure survives the scrutiny, that the larger catalogues and better maps of the coming years confirm it is genuinely there. What then? What actually breaks if the largest structure in the universe is real? The answer reaches much further than one strange object in one corner of the sky, and it touches the foundations of nearly everything we claim to know about the cosmos. Part 8. What breaks if it is real? Let us grant the structure its reality for the length of this part and follow the consequences honestly, because they are larger than most people realize. It is tempting to think that even if the Hercules and Corona Borealis structure is real, it is just one more entry in a catalogue, an impressive curiosity that specialists can argue about while the rest of cosmology carries on undisturbed. That is not the case. If this structure is genuinely there, the thing it threatens is not a detail. It is the load-bearing wall of the entire building. Return one more time to the cosmological principle, the rule we started with, the assumption that the universe is smooth and the same in every direction once you pull back far enough. I have called it a promise and a comfort, but it is also something more practical and more powerful. It is the assumption that makes the mathematics of cosmology possible at all. When physicists write down the equations that describe the whole universe, the equations that tell us it is expanding, that let us trace its history back to the Big Bang and forward to its eventual fate, they begin by assuming smoothness and sameness. That assumption is what lets them treat the universe as a single thing with a single history, rather than an impossibly complicated patchwork that would have to be solved point by point forever. Smoothness is not just a nice property of the cosmos. It is the simplification that turns an unsolvable problem into a solvable one. So if the universe is genuinely lumpy on the larger scales, if there are real structures so big that the smoothness assumption fails right where we need it most, then the foundation of that mathematics develops a crack. The equations would still work as an approximation, the way the assumption that the Earth is flat works just fine for laying out a garden. But we would have to admit that our description of the universe as a whole rests on an approximation that breaks down at the larger scale, and that admission would ripple outward into nearly everything we measure. Consider how we study dark energy, the mysterious something that is causing the expansion of the universe to accelerate. We measure it by assuming the universe is smooth, and comparing how it has expanded over cosmic time against models built on that assumption. If the smoothness is not real on the larger scales, then those comparisons inherit an error we did not account for, and our confidence in what dark energy is doing softens. Consider the very claim that the universe has no centre and no edge. That claim is a direct consequence of the cosmological principle. Weaken the principle, and you reopen questions we thought were permanently closed. Questions about whether there might be preferred directions in space, whether one part of the cosmos might be genuinely different from another, whether the universe might have a structure on the larger scales that we have been trained by our own assumption not to look for. I do not want to overstate this, because overstating it would be its own kind of dishonesty. Even if the structure is real, it is more likely that it signals a missing ingredient in our model than a total collapse of the model. The Big Bang picture rests on several independent pillars: the ancient glow of light from the early universe, the observed abundances of the lightest chemical elements, the expansion itself, and those pillars are not going to vanish because of one oversized structure. The most probable outcome, even in the scenario where the structure is real, is not that cosmology is wrong, but that cosmology is incomplete, that there is something about how structure grew in the early universe, or about the nature of dark energy, or about the behavior of gravity on the larger scales that we have not yet understood. The structure would be a clue to that missing piece, not a wrecking ball through the whole edifice. But a clue to a missing piece of our model of everything is not a small thing. That is precisely the kind of clue that, historically, has preceded the largest revolutions in our understanding. The strange wobble in the orbit of Mercury was once just an annoying discrepancy, a tiny error in the tables, until it turned out to be the first sign that Newton's gravity was incomplete and Einstein's was needed. The faint uniform hiss of static that two engineers could not get rid of in their antenna turned out to be the afterglow of the Big Bang itself. Anomalies at the edge of a successful theory are not embarrassments to be swept away. They are the places where the next understanding tends to be hiding. If the Hercules and Corona Borealis structure is real, it may be one of those places, a discrepancy that looks like a nuisance now and turns out, in some future textbook, to have been the first crack through which a deeper picture of the universe came pouring. To feel why the smoothness assumption is so load-bearing, it helps to imagine trying to do cosmology without it. Suppose the universe really were lumpy on the larger scales, genuinely different in different directions, with no scale at which it settled into sameness. Then there would be no single answer to a question as basic as how fast the universe is expanding, because the answer might depend on which way you looked and where you stood. There would be no clean history to run backward to the Big Bang, because different regions would have different histories. The universe would become a problem of staggering complexity, an unsmoothable patchwork that no equation could capture as a whole. The reason cosmology is a science at all, the reason we can say anything confident about the universe as a single object with a single story, is that smoothness lets us replace an impossible patchwork with one tidy, solvable description. Pull that assumption, and you do not just lose a detail, you lose the ability to treat the universe as one thing. It is also worth being clear about what would and would not survive. The expansion of the universe would survive, because we see it directly in the light of distant galaxies, stretched toward the red as they recede. The ancient glow left over from the early universe would survive, because we detect it filling the sky. The cooked-up abundances of the lightest elements forged in the first few minutes would survive, because they match the predictions beautifully. These pillars do not depend on the finest details of how structure grew, so even in the scenario where the larger structure is real and the smoothness assumption needs revising, the broad story of a hot, dense beginning that expanded and cooled would remain standing. What would change is the chapter on how structure assembled, and possibly the chapter on what dark energy is, and possibly the chapter on how gravity behaves across the greatest distances. Those are not small chapters, but they are chapters, not the whole book, and it matters to say so plainly rather than reaching for the easy drama of a universe in ruins. History gives us real reasons to take this seriously rather than dismissing it as overreach. Twice in the last century, a small and stubborn discrepancy that most people wanted to ignore turned out to be the doorway to a deeper theory. The tiny, inexplicable drift in the orbit of the planet Mercury sat as an irritating footnote for decades, until Einstein's new picture of gravity explained it exactly and overturned our understanding of space and time in the process. The faint background hiss that two engineers kept finding in their radio antenna, which they first blamed on pigeons and dirt, turned out to be the afterglow of creation itself. In both cases, the anomaly was small, easy to wave away, and far more important than anyone first suspected. The largest structure in the universe may be nothing of the kind. But the history of science is a history of small anomalies that turned out to be doors, and a careful mind keeps that in view without letting it become a certainty. There is a deeper irony worth sitting with here, which is that the cosmological principle was always, in part, an act of faith dressed as an assumption. In the early days of modern cosmology, we could not actually verify that the universe was smooth on the larger scales, because we could not see far enough or measure enough galaxies to check. So the smoothness was adopted partly because it was reasonable, and partly because, without it, the mathematics was simply impossible to do. It was a necessary simplification, a bet that the universe would turn out to be as tidy as our equations needed it to be. For decades, that bet has paid off handsomely, confirmed by the evenness of the ancient glow and the broad uniformity of galaxy surveys. But a bet is still a bet, and the largest structure in the universe is the universe quietly asking whether we are sure we want to keep the wager on the table. Most likely the bet still holds, and smoothness survives with only minor revisions. But it is worth remembering that the most fundamental assumption in cosmology began life as the thing we needed to be true in order to proceed, and the line between what we need to be true and what is actually true is a line every honest scientist learns to watch with great care. And this is the moment to admit something that should make the hair on your arm stand up a little, gently, the way a good ghost story does rather than a nightmare. The structure traced by the gamma-ray bursts is not the only thing whispering that our model might be incomplete. While the argument over the largest structure in the universe has been unfolding at the scale of billions of light years, a completely different kind of telescope, looking at a completely different kind of object at the opposite end of the scale of size, has been finding its own impossibilities. And the two sets of impossibilities, though they come from utterly different directions, seem to be leaning toward the same uncomfortable suspicion. To see how, we have to leave the larger scales behind for a while and look instead at the very small and the very early, at the things a new and extraordinary telescope has been finding in the first chapters of cosmic history. Part 9. The Other End of the Scale. There is a name in our title that I have been holding in reserve, and now it is time to be honest and careful about it, because honesty about it is more interesting than the easy version. The title of tonight's journey invokes the James Webb Space Telescope, the most powerful eye humanity has ever lifted into space, and I owe you the plain truth, which is that the James Webb Space Telescope did not find the Hercules and Corona Borealis structure. It could not have. That structure was traced by gamma-ray bursts, by the older satellites that catch those flashes, long before Webb ever opened its golden mirror. So if you came tonight expecting that Webb pointed itself at the largest structure in the universe and photographed it, I have to set that expectation gently aside. But here is why Webb belongs in this story anyway, and why its presence makes the mystery deeper rather than thinner. Webb has been doing something at the opposite end of the scale of size that rhymes, uncomfortably, with what the largest structure is hinting at. Webb was built to look further back in time than any telescope before it, to catch the faint light of the first galaxies forming in the early universe, light that has been travelling toward us for almost the entire age of the cosmos. And when Webb opened its eye on that early universe, it found something nobody was fully prepared for. It found galaxies that were too big, too bright, and too mature, far too early. In the standard story of how the universe assembles itself, the same story we told in Part 5, galaxies are supposed to start small and grow slowly, building up over billions of years as gravity gathers their stars and gas. The early universe should be a place of small, scrappy, unfinished galaxies, just beginning the long work of becoming something grand. But Webb kept finding the opposite. It found galaxies in the first few 100 million years after the Big Bang that were already massive, already structured, some of them already finished with their star formation, already old and quiet in a universe that was supposed to be far too young to contain anything old and quiet. We have spoken on this channel before about these early dead galaxies, these objects that had already lived their lives and settled into stillness when the universe was barely out of its infancy. Webb keeps finding structure and maturity arriving too early. The same phrase, the same suspicion that haunts the largest structure in the universe. Do you feel the shape of it? At the scale of billions of light years, the gamma-ray bursts hint that the universe assembled structure too large and too early for our model to allow. And at the scale of individual galaxies, Webb finds that the universe assembled them too big and too early for our model to allow. These are completely independent lines of evidence. Different objects, different telescopes, different methods, different scales separated by a factor of millions. They have no business agreeing with each other, and yet they seem to be leaning the same way, both of them murmuring that the early universe built its contents faster than the rules predict, that structure came together more quickly and more completely than the patient slow gathering of gravity should permit. They are separate cracks in separate walls, but when you stand back you realize they face the same room. Now I want to take you somewhere, the way we sometimes do on quiet nights like this, into the structure itself, because there is one final strange truth about it that only becomes clear when you imagine standing inside. Picture yourself placed at the very centre of the Hercules and Corona Borealis structure 10 billion years ago in the young universe. You've been told you're standing in the middle of the largest object that exists, a thing 10 billion light years across, a structure so enormous it may break the rules of cosmology. So you look around and you brace yourself for grandeur. You expect a wall, you expect a glow, a wash of light, a density you can feel pressing in from every side, some sign that you're inside something colossal, and you find nothing. You find ordinary space. There are galaxies scattered around you, yes, but they are spread thin, separated by the same enormous gulfs of darkness that separate galaxies everywhere. Look in any direction, and you see what you would see from almost anywhere in the cosmos, a scattering of distant light across an immensity of black. There is no wall to put your hand against. There is no edge, no glowing boundary, no rumble of the structure's vastness. The thing you are standing inside of is so large that no observer inside it could ever perceive it at all. Its enormity does not exist at the scale of a galaxy, or a star, or a single conscious being looking around in wonder. It exists only in the statistics, only when you pull back across billions of light years and count the galaxies and notice that here, in this immense region, there are a few more than there should be. The largest object in the universe is invisible from within. You could spend an eternity inside it and never know it was there. It can only be seen from outside by something that can hold 10 billion light years in a single glance and notice the faint excess in the count. It can only be seen, in other words, the way we are trying to see it now, from impossibly far away, through the depths of stars, at the very limit of what our instruments and our statistics can manage. The reason Webb can look so far back in time deserves a moment, because it is one of the genuine marvels of our age. Light travels fast, but it does not travel infinitely fast, and across cosmic distances its finite speed turns every telescope into a kind of time machine. When Webb gathers the light of an extremely distant galaxy, that light has been travelling for well over 13 billion years, set loose when the universe was only a few % of its current age. So Webb is not seeing those galaxies as they are. It is seeing them as they were in the first chapters of cosmic history, their ancient light only now arriving after a journey nearly as old as time. To build a telescope capable of catching that light, Humanity had to fold a mirror the width of a tennis court, launch it 1,000,000 miles from Earth, and chill its instruments to within a few degrees of the coldest temperature physically possible, all so that the faint warmth of the first galaxies would not be drowned out by the telescope's own heat. It is, in a real sense, the finest instrument our species has ever made for the purpose of looking backward in time. And what it found, the too early and too mature galaxies, is worth holding alongside the larger structure with real care, because the comparison is suggestive without being identical. These are not the same phenomenon. One is about the overall arrangement of matter across billions of light years. The other is about how quickly individual galaxies grew up. They could, in principle, have completely separate explanations, and it would be a mistake to weld them together into a single story before the evidence justifies it. But there is a thread that could plausibly run through both, and the thread is the suspicion that the early universe built its contents faster than the slow gathering of gravity, working alone from the standard seeds, should allow. If that suspicion is correct, it would touch the overlarge structure and the overmature galaxy from the same root. The idea that the early cosmos had a head start we have not accounted for. The honest position is to notice the rhyme between these two mysteries without insisting they must be the same poem. There is a quiet vertigo in realizing that two of our finest windows on the universe, one watching the deaths of giant stars across the larger scales, the other catching the birth of galaxies in the earliest times, are both returning the same uneasy report. They were built by different people for different purposes. They look at different things. They have no reason to agree. And yet both of them, in their separate ways, keep handing back the same word, early, the same sense that the universe assembled itself ahead of schedule. It may be coincidence. It may be that one or both reports will dissolve under closer scrutiny. But for now there are two cracks in two very different walls, and when you stand in the middle of the room and look from one to the other, it is hard not to feel that they are facing each other across the same hidden space. It is worth being precise about how different the two scales really are, because the agreement between them is what makes the rhyme so unsettling. The larger structure is measured in billions of light years, a scale that contains uncountable galaxies. The early galaxies Webb studies are individual objects, each one a single galaxy among that uncountable multitude. The difference in size between the two is itself almost beyond comprehension, a factor of many millions, the difference between a single grain of sand and an entire continent of beaches. There is no obvious physical reason that a mystery about the arrangement of matter across continents of beaches should have anything to do with a mystery about how quickly a single grain of sand formed. And yet both mysteries seem to be pointing at the same suspect, the idea that the early universe assembled its contents faster than our patient gravitational accounting allows. When two clues separated by a factor of millions in scale, found by different instruments built for different purposes, both seem to accuse the same culprit, a careful investigator does not assume they are connected, but a careful investigator does not look away either. And that strange fact, that the biggest thing there is can only be seen from outside and never from within, turns out to be the key to the last part of our story. Because the question is no longer simply whether the structure is real. The question is what kind of thing it would have to be to exist at all, and there are several answers on the table, several ways the universe might be allowed to build something this large without breaking everything we hold dear. Some of those answers rewrite the early universe, some rewrite gravity itself, and one of them, the quietest of all, suggests that the structure is real, but that we have been describing it wrong from the very beginning. Part 10. The Ways. The universe could still win. Suppose we take the structure seriously. Suppose the larger catalogues and sharper maps of the coming years confirm that it is genuinely there. A real concentration of matter 10 billion light-years across in the young universe. We have spent this whole journey describing why that should be impossible, why the finite age of the cosmos and the finite reach of gravity forbid anything so large. So how could it exist anyway? The remarkable thing is that physicists already have several candidate answers, several ways the universe might be allowed to build something this enormous without the whole picture falling apart. None of them is proven, but each one is a door, and it is worth opening each of them just enough to see what kind of room lies behind. The first door is the gentlest. Perhaps the cosmological principle is true. The universe really is smooth on the larger scales, but the scale at which that smoothness takes over is larger than we assumed. In this version, the end of greatness is real but sits further out than the textbooks place it. Structures the size of the Hercules and Corona Borealis complex would then be rare, the once-in-a-cosmos giants at the very upper limit of what is allowed, but not forbidden. The trouble with this door, as we have already seen, is the staircase of other oversized structures. If giant structures were merely rare, we would expect to find very few of them, and we keep finding them. The more of them turn up, the harder it becomes to call them rare exceptions, and the more they start to look like a feature of the universe we have not accounted for. Still, the door is open. It may simply be that the universe is permitted to be lumpier than we believed, and that we drew the line of smoothness in the wrong place. The second door is more dramatic, and it leads back to the early universe. Perhaps structure grew faster than the slow gathering of gravity allows, because the seeds it grew from were not quite what we assumed. Remember that everything began from tiny ripples in the density of the early cosmos, faint regions slightly denser than average that gravity then amplified over billions of years. We have a standard expectation for how those ripples were distributed, how many large ones and how many small ones there should have been. But what if that expectation is slightly wrong? What if the early universe laid down a few more large-scale ripples than the standard recipe predicts, giving gravity a head start on building enormous structures? Physicists have a technical name for departures from the standard recipe, and they search for them carefully, because even a small deviation in the initial seeds could allow much larger structures to form much earlier than the basic model permits. This is the same family of explanation now being whispered about Webb's two early galaxies. If the seeds were richer than we thought, then both the overlarge structure and the overmature early galaxies might be telling us the same thing, that the universe was handed a head start we did not know about. The third door reaches all the way down to the rules themselves, to gravity, and to the dark energy that fills space. Our entire calculation of how fast structure can grow depends on our theory of gravity and on the particular history of the universe's expansion. Change either of those, and the speed limit changes too. There are serious proposals in which gravity behaves a little differently on the larger scales than Einstein's theory predicts, and proposals in which dark energy was not always the steady presence it appears to be today, but switched on, or changed its strength, in the early universe. Under some of these modified histories, matter could clump faster, and structures could grow larger than the standard model allows. A structure that is impossible under one set of rules becomes ordinary under another. This is the most radical door, because walking through it means admitting that our theory of gravity, or our understanding of dark energy, is incomplete in a way that matters. But our theory of gravity and our understanding of dark energy are already known to be incomplete in other ways. We do not know what dark energy is. We do not know how to reconcile gravity with the quantum world. It is not absurd to wonder whether the largest structure in the universe is pointing at the same gaps from a new direction. And then there is the fourth door, the quietest one, the one that does not require rewriting the early universe or the laws of gravity at all. Perhaps the structure is real, but we have been describing it wrong. When we say structure, we tend to imagine something coherent and bound, like a galaxy cluster held together by its own gravity, or even like a physical wall you could in principle press against. But the Hercules and Corona Borealis complex may be neither of those things. It may be a genuine overdense region of the cosmic web, a place where the great threads and sheets of galaxies happen to run thicker than average, without being a single object bound together by gravity into one coordinated whole. It would still be real. It would still be a concentration of matter larger than we expected. But it would not be a single thing that gravity had to assemble across 10 billion light-years all at once, which softens the paradox considerably. The speed limit we worried about applies to building bound, coordinated structures. A loose overdensity, a region where the web is simply denser, does not have to have been pulled together as one piece. In this reading, the structure is impressive and suggestive and worth every bit of our attention, but it is not quite the rule-shattering monster the headline implies. It is enormous and loosely organised rather than enormous and solid. Notice what all 4 doors have in common. Not one of them is a door marked "the universe is broken and nothing makes sense." Every single one is a door marked "we have more to learn." That is the texture of real science at its frontier. The choices are not between a comfortable known and a terrifying unknown. The choices are between several flavours of we do not yet fully understand, each of which, if we walked through it, would teach us something new about the cosmos, about its beginnings, about the forces that shape it, or about the humble matter of what we even mean by a thing. And which door is the right one, if any of them is, we cannot yet say, because the deciding evidence has not yet arrived. It is worth saying clearly that having several candidate explanations is a sign of health, not confusion, even though it can feel unsatisfying to be handed 4 doors and no key. In a mature science, a genuine anomaly does not usually arrive with a single obvious cause attached. It arrives as a puzzle that several existing ideas might solve, and the work of the coming years is to test those ideas against sharper data until all but one of the doors closes. We are in the early part of that process now, the part where the possibilities are still open, and the evidence cannot yet rule between them. That openness is not a weakness in the story. It is the story caught in the middle before the ending has been written, and there is a particular pleasure in watching a real mystery at exactly this stage, when the universe has posed the question clearly, but has not yet let slip the answer. Each of the 4 doors, notice, would teach us something we genuinely want to know. If the smoothness scale is simply larger than we thought, we learn that the universe is lumpier than our textbooks, and we redraw the boundary of greatness further out. If the early seeds were richer than the standard recipe, we learn something profound about the first instance after the Big Bang, about the quantum fluctuations that became everything. If gravity or dark energy behaves differently than we assumed on the larger scales, we touch the 2 greatest unsolved problems in all of physics from a new direction. And if the structure is real but merely a loose overdensity rather than a bound object, we learn to be more careful about what we mean by a thing, which is its own kind of wisdom. There is no door that leads to a dead end. Every one of them opens onto a room with something worth finding in it, which is perhaps the most hopeful thing about this entire mystery. There is a particular discipline required to sit with 4 open doors and resist slamming 3 of them shut out of a hunger for a clean answer, and it is worth naming that discipline, because it is the quiet engine of all good science. The temptation, always, is to pick the most exciting door, the one that promises new physics and a revolution, and to declare it the answer before the evidence has earned that declaration. The opposite temptation is just as strong, to pick the safest door, the one that says it is probably just an artifact, and to dismiss the mystery so we can stop being unsettled by it. Both temptations are forms of impatience, and both have led careful people astray throughout the history of science. The harder and more honest path is to hold all 4 doors open at once, to give each its fair weight, to design the observations that could distinguish between them, and to wait. That waiting is not idleness. It is the most active and demanding thing a scientific mind can do, to remain genuinely uncertain in the presence of a question that aches to be answered, until the universe itself supplies the evidence to close all but one of the doors. But it is coming. New surveys are being built and switched on right now that will map the positions of many millions more galaxies, and catch many more gamma-ray bursts, and trace the structure of the cosmos across enormous volumes with a precision we have never had. Within the coming years, those surveys will deliver a verdict that the small, noisy catalogues of today cannot. They will either confirm that giant structures keep appearing past the ceiling, in which case one of these doors will have to be walked through in earnest, or they will reveal that the giants were illusions cast by our uneven view, and the smooth universe will quietly reassert itself. Either way, we're about to know something we do not know tonight. And that brings us to the last and largest question of all, the one this entire journey has been circling, the question of what the largest structure in the universe is really a measurement of. Part 11. A flaw in the map, or a flaw in the map maker. We have come a very long way tonight, from a quiet rule that almost nobody talks about, through the deaths of giant stars, out to a structure 10 billion light-years across that may or may not be there, and we arrive now at the question that has been waiting underneath all of it. When we look at the Hercules and Corona Borealis structure, what are we actually looking at? And I want to suggest that there are, in the end, two ways to understand what this thing is. Two interpretations that sit beneath all the technical doors we just opened, and that the difference between them is one of the most quietly profound choices in all of science. The first interpretation is that the structure is a flaw in the map. By that I mean it is a genuine feature of the universe that our map of the cosmos failed to predict, a real thing that our model said should not be there. If this is the case, then the structure is a clue, perhaps one of the most important clues of our generation, that our model of everything is incomplete. The map we drew of the universe, beautiful and successful as it is, would be missing something at its larger scales, and this structure would be the place where the missing piece pokes through into view. That is the thrilling interpretation, the one where the universe turns out to be stranger and richer than our theories, where there is genuine new physics waiting in how the cosmos built its largest structures, and where a few dozen flashes of ancient light were the first hint of a deeper truth. The second interpretation is gentler and in its own way even more humbling. It is that the structure is not a flaw in the map at all, but a flaw in the map maker. By that I mean that the structure may be telling us less about the universe than about ourselves, about the limits of our instruments, the unevenness of our vision, the smallness of our samples, the way we can mistake the shape of our own attention for the shape of the cosmos. In this interpretation, there is no rule-breaking monster out toward Hercules and Corona Borealis. There is only a smooth universe, behaving exactly as the cosmological principle promised, and a young, eager species that looked at it through a flawed and uneven window and saw a wall that was never there. The largest thing we ever found would turn out to be a portrait of our own limitations, a measurement not of the universe's lumpiness, but of our ability to fool ourselves. Here is what I find genuinely beautiful, and I mean that word carefully. Both of those interpretations are acts of humility. One says the universe is larger than our model, that the cosmos has more to teach us than we have managed to learn, that reality outruns our equations. The other says our seeing is smaller than we think, that our instruments and our statistics and our hunger for patterns can lead us astray, that we must be forever willing to doubt our own most exciting results. The structure forces us to choose, for now, between two kinds of smallness, the smallness of our theories against the universe, or the smallness of our vision against the truth. And there is no shame in either. To do science honestly is to live in exactly this tension, to hold a spectacular possibility in one hand and a ruthless doubt in the other, and to refuse to let go of either until the evidence forces your grip. Think back to where we began, to that half-joking phrase the astronomers gave to the scale where the lumps were supposed to run out, the end of greatness. We started the night treating it as a settled fact, a milestone, the boundary beyond which the universe goes smooth, and there is nothing larger to find. But look at the phrase now, after everything. Maybe greatness has not ended. Maybe the universe is still building structures larger than we allowed, and the end of greatness was only ever the end of what we expected, not the end of what is. Or maybe greatness ended exactly where we said it did, and the structures we keep finding past that line are mirages we drew ourselves, in which case the phrase holds, and the largest real things in the universe are smaller and humbler than the giants we keep imagining. The same three words mean opposite things depending on which interpretation is true, and we do not yet know which it is. The phrase has become a question, and so we are left holding the largest object ever found, and a ruler we are no longer sure we can trust. That image deserves to be the last one we sit with tonight, because it is the truest thing in the whole story. Every map of the cosmos is also a map of our ability to make maps, Every measurement of the universe is also a measurement of the instrument that took it. When we look out at the farthest, largest, oldest things, we are always, unavoidably, also looking at the limits of our own seeing, and it is not always easy to tell where the universe ends and our instruments begin. The Hercules and Corona Borealis structure is the place where that ambiguity becomes impossible to ignore, where the biggest thing we ever found might be a message about the smallness of how we found it. We have been measuring the cosmos with a ruler that may bend in our hands without our noticing, and the largest structure in the universe is what showed us the ruler might be bending. Before we let the night settle toward its close, I want to return one last time to the gamma ray bursts, because there is a tenderness in them that ties the whole story together. Every pin in the map that may or may not show the largest structure in the universe is a star that died, a giant that collapsed and fired its final brilliance across 10 billion years of space, so that, by pure improbability, it could arrive at a detector built by curious creatures who would use it to ask whether the universe has a shape. There is something almost circular and lovely in that. The deaths of the oldest giants become the means by which the youngest civilization we know of interrogates the cosmos. The light of endings becomes a tool for beginnings of understanding. Whatever the structure turns out to be, the method itself, mapping the universe by the last words of dying stars, is one of the strangest and most beautiful things our species has ever learned to do. And there is a comfort, I think, in ending without an answer, though it runs against every instinct that wants the mystery solved tonight. We live in a time that prizes certainty, that wants every question closed and every verdict delivered. But the larger scales of the universe are not in a hurry, and neither, in the end, should we be. The structure out toward Hercules and Corona Borealis has waited 10 billion years for its light to reach us. It can wait a little longer for us to understand it. The surveys are coming, the catalogues are growing, the verdict will arrive, in years rather than lifetimes, and when it does it will teach us either that the universe is stranger than our model, or that our seeing was smaller than we believed, and both of those lessons are worth waiting for. Until then, we are allowed to do the gentlest thing a mind can do with a great question. We are allowed to hold it lightly, to turn it over in the dark and to let it be enough, for one quiet night, simply to wonder at a universe still generous enough to keep a secret this large. There is a final symmetry worth noticing as we draw toward the quiet end of all this. We began the night with a rule that promised the universe has no centre, that no place is special, that wherever you stand you are ordinary and therefore at home, and we are ending with a structure that, if it is real, does not actually overturn that comfort so much as deepen it into something richer. For even a lumpy universe, a universe with structures larger than we expected, can still be a universe without a centre, still a universe where you're not standing at any edge, still a universe that greets every observer as one of its own. The largest structure does not threaten to put us back at some cosmic middle, or to find us a special place. At most, it tells us the cosmos is more textured, more surprising, more generous with its greatness than we assumed. And there is a kind of peace in that, the peace of belonging to something that is both endless and still capable of astonishing the minds it produced. Whatever the verdict turns out to be, we remain small observers on a small world, reading the light of dying giants, asking the largest question we know how to ask, and that smallness, held in the right way, is not a sorrow. It is a privilege, and it is enough. That is not a frightening thought when you let it settle. It is a humbling one, and humility, in the face of something this large, is a kind of peace. Whatever the structure turns out to be, real feature or beautiful illusion, it has already done something valuable. It has reminded us that the universe is still bigger than the model, that there are questions at the larger scales we have not closed, that the cosmos has not finished surprising us and may never finish. The smooth, comfortable universe we started with is still mostly intact, still the best description we have, still the reason you're not standing at the edge of anything. But there is a structure out there, in the direction of a constellation, and the little crown beside it, that keeps the question open, and there is something gentle and right about ending a night not with an answer, but with a question that the universe itself has not yet chosen to answer. We will know more soon. The surveys are coming, the catalogues are growing, and until they speak, we get to do the rarest and most peaceful thing a curious mind can do. We get to sit quietly with the largest mystery there is, and simply wonder, without needing, just yet, to be sure.